Part C, exact ODEs. Yeah. This method, I think most of you have learned before, but here we review it. When we go through, we can review, try to understand some basics better. Now, especially, we want to understand that differential concept better. Yeah. All right, C.1, exact ODEs. Yeah. So let's look at the new method. Yeah. So we want to, add a new problem-solving tool in our toolbox. Yeah. All right. So this time we try to use a different view to look at the ODE. Yeah. So let's look at the general form. So this is an explicit first order ODE form, very general. Yeah. For the ODE like this, the general case, most of the ODEs, we may not be able to find the solutions. Yeah. Only a small portion of it, we can find a solution. So that's the reason we usually consider the special cases. Yeah. So far at this point, we consider the decay model. That's a special case, right? After that, we consider separable ODEs, also special case, right? So after that, extended separable ODEs. Yeah. So all special cases. Yeah. And here, we need to consider another type of special case. Yeah. So we want to consider those f function that has this fractional form. The numerator function is m function with two variables, x and y. Denominator function, another function, we call the n function with x, y variables. Yeah. All right. So when we write f function in this fractional form, naturally, so you can see, we write the derivative also in this fractional differential forms, dy over dx. It's a fraction. You can treat it as a fraction, dy over dx. Yeah. Then we can change its form. Yeah, we know. So we can remove the common denominator. So we can, do some transformation on this form. Yeah. So here we want to look at the special property. Yeah. Yeah. So there is an important concept related to this method. Yeah. So that is called a total differential concept. Yeah. We learned the general differential concept. Yeah. But here, the total differential, a slightly different meaning. So what's the total differential concept? Yeah. So let's consider an explicit function or curve with the form u of x, y equals constant c. This form. Yeah. And if we write a function or curve, so we can draw a curve on the plane. In this way, we call it implicit function, right? So the function in this way, we call it implicit. function. Yeah. Because it may not be easy to write it as an explicit function. Explicit function is y equals f of x. Now, if you can write y equals f of x, then it's an explicit function. Yeah. But many times we cannot convert an implicit function to another explicit function. Yeah. Very hard, impossible to do that conversion. Yeah. And so you can treat this explicit function, you can treat it as a special case. Special case. Okay? Yeah. Implicit form is more general than explicit form. Yeah. Yeah. Because in the explicit form, only a small portion of it can be converted to explicit form. Yeah. The most part cannot be converted to an explicit function form. Yeah. All right. So here you can see we extend our consideration from explicit form to implicit form. Yeah. So our consideration is larger here. Okay? Yeah. A little larger. Yeah. So this time we consider equation. So this equation is going to be the solution of an ODE. Okay? Yeah. So far, our solution has this form, right? Yeah. Explicit function, y equals a function, so far. Yeah. But that is too limited, right? That form is very limited. Now, we want to enlarge the possibility. Yeah. Because many times it is impossible to use an explicit function as the solution of an ODE. Yeah. Many times it's impossible. Okay? So now we want to enlarge the possibility. Yeah. Extend the solution format from an explicit form to an implicit form. So we can cover more cases, right? Yeah. So we can do more than before. Yeah. So that's the reason why we consider this implicit function form as the target solution of our ODEs. All right? Yeah. All right. So with this background, now you understand. Yeah. So why we go this way. Yeah. So with this background, now let's continue. Yeah. First, we consider one simple, commonly seen curve. It's a circle, right? We know this is the function for a circle, a standard circle, unit circle. People also call it unit circle because the radius is 1. The radius of the circle equals 1. Yeah, this is 1. Okay, 1 square radius. Yeah, unit circle. Yeah. All right. Here you can see this is an implicit function. Yeah. Here we call this implicit function. Okay? All right. But some people may argue, yeah, because this equation is so simple, so we can represent it as an explicit function easily, right? Yeah. But if you want to represent it as an explicit function, you need to be a little careful. So when you write y as a f function, here there are two functions, plus minus root 1 minus x squared. So it's not one function. There are two functions. Yeah. All right. Yeah. One above the x-axis, one below the x-axis. Yeah. So the negative part, positive half, and positive half circle, negative half circle. You have two half circles. All right. Yeah. So you put these two half circles together, so you get a full circle. Okay, so if you want to write it as an explicit function, yeah. But this example is so simple, so you can write it as an explicit form. But for the most other implicit functions, you cannot write it as an implicit function. Yeah. All right. So that we just take it. We just accept implicit function representation as our solutions for the ODEs. Here. Yeah. So now we understand in that way. Yeah. So because I want to answer your doubt, your possible doubt, why we use the implicit function format to represent solutions to the ODEs. Yeah. The answer is because we want to do more. We want to cover more cases. Yeah. So we want more flexibilities, more possibilities. Okay. All right. So let's continue. All right. Then, because in this form, we can take a differential on the curve, both sides, right? Yeah, because it's an equality. Yeah, it is an equality. So we can take differential, that d, little d, both sides of the equation, right? Yeah. So when we do that, you can see when we do d, apply d operation, both sides of that u equation, so we get du equals 0, because the constant c, when we apply the differential on constant c, we get 0. Okay, we get 0. Yeah, because the derivative of c is 0. Okay, yeah, so its differential is also 0. Yeah, all right. So now you can see du equals 0. Du equals 0. All right. Yeah. All right. Yeah. But here, so what's that total differential, right? Yeah. So this time I need to explain this total differential concept. Yeah. Why you have this total word? Total. This special word here. Okay. All right. Yeah. Yeah. The reason is this. Yeah. All right. Here, this u function, let's look at the u function. U function has two variables, x variable and a y variable. All right. Yeah. X variable, y variable. So then, regarding the x variable, yeah, because when you have a function, u function, it's a function of two variables, x and y. Okay, all right. Now let's think about when we take a derivative on this function. When we take a derivative, we can only select one variable to take a derivative, right? Yeah. Yeah. So think about, yeah. Now, in order to do d around this two variable function, yeah, we know when you take the differential, you need to go through derivatives, right? Yeah. So remember, we use derivatives. So differential of y equals the derivative y prime times dx, right? Yeah. If y is a function of x, y is a function of x, okay? Yeah. But this time, u is a function of two variables, x and y. Yeah. All right. So when you take a differential, you need to use a special derivatives. We call it partial derivatives. Yeah. Here we need to introduce the partial derivative. Look at the, the special notation, partial derivatives. When you do partial derivatives, you need to select one variable. Okay. All right. So the first type of partial derivative, partial u over partial x, you make x as the variable. When you make x as a variable, everything else is treated as constant. Okay? All right. And the second time, when you do partial derivative with respect to the y variable, so this time y is the variable and everything else is the constant. That's the way people do partial derivative. Yeah. So there is a formula in calculus. If u is a two-variable function with respect to x and y, then when you take a differential d on u function, then you can use this partial derivative representation. Partial u over partial x times dx plus partial u over partial y times dy. Okay? Yeah. So you may ask me why, right? Yeah. So I remember in class, Lucas asked me to explain why it is correct. Yeah. So to answer that question rigorously, you need to go back to the calculus textbook. Yeah. There is a proof why. The proof we go back to the definition of the derivative, differential derivative, the definition. Okay, yeah. So you need to do a lot of work, yeah, so you can get this formula. Yeah. Here I do not plan to go through that rigorous proof. Yeah, but I plan to do one thing. Yeah, I will select a concrete example and use that example to convince you this formula makes sense. Yeah, I will do it next time. Yeah, later sometime. Yeah, later sometime. Yeah, but not here today. Yeah, yeah. At this point, you just accept this formula. Okay. Yeah, just take it. Yeah, and use it. Yeah. All right. So here you can see, because du has this form. If we look at the right-hand side, okay, right-hand side, this right-hand side representation, if we start with the right-hand side representation, yeah, because it can be represented as the du, so then that's the reason we call the right-hand side differential representation as a total differential. Yeah. The reason is it can be written as 1 du form. Yeah. If the right-hand side cannot be represented as the 1 du form, then we cannot call it total differential. Okay? Yeah. So here you understand the meaning. Yeah. So with this background, now we can go back to our current new consideration of the ODE. Y prime equals that special fractional form. Two variable functions in numerator and a denominator. All right. Now, we just do the equivalent transformation. So this is equivalent transformation, right? Yeah. Cross product. Then change this, move terms to the same side. So we get this equivalent form. Yeah. All right. Yeah. But when we work on this form, we want to target our existing knowledge. Okay? Yeah. So we have that background. So we discussed. We spent a lot of time to understand that total differential background knowledge. Why we do that? Because we want to make connection. Yeah. All right. So this new form, looks somewhat related to the total differential form, right? Yeah. Somewhat related. Yeah. So we want to establish some connection between them. Okay. All right. So when we compare these two formulas by their forms, so we see a lot of similarity, right? Yeah. It's, for example, some function multiply dx differential, and there is a second term, another function multiply dy differential, right? So here we have dx part and a dy part. Yeah. All right. So then, but in this m and formula, we use that negative sign. Yeah. But the negative sign is not something that we cannot overcome, right? Yeah, the negative sign can be easily converted to the plus sign because in this total differential form, it's a plus sign. Yeah. So if we want to move this, our current form to the total differential form. But when we do that, we need to change this minus sign to plus sign. Yeah. So that's very easy. We can just use plus minus n function, right? Yeah. How about we can make that n function negative? Yeah. So then we get a plus sign. Yeah. So we can change that easily. Yeah. In that way, so you can do analogy, right? Yeah. So the plus sign, both use plus sign in the middle. Yeah. All right. So then we can consider, because we just do negation on n function. If we do negation on n function, then we have plus sign here, right? Yeah. So the negation thing, easy. How about when we write f function, how about we add that negative sign, right? If we really need that plus sign, we add that, or we write a negative sign in front of this fractional form. How about that? Yeah, that's easy. Yeah. So in that way, we fix that negative sign problem. Yeah. Then we try to match. Yeah. M function should correspond to partial u over partial x. M function should correspond to partial u over partial y function. Right? Yeah. All right. Yeah. Yeah. So in that comparison, so we want to, so here, so this last formula we want to understand in this way. In order to make the left-hand side expression, in order to make it a total differential. So our goal to make it total differential, okay, we need to find some u. We need to find appropriate u such that m function equals partial u over partial x, m function equals partial u partial y function. How about that? If you can find such u, then your conclusion is the left-hand side expression is a total differential. If it is a total differential because you find that u, then you, based on the du equals 0, yeah, because du, now you have du equals 0, right? So you go back, you can write your solution of your differential equation, u of x, y equals c. You're just going back. You get a solution in the implicit form, right? Yeah, that logic. Yeah. So now you can see we need to find appropriate u. Yeah. All right. But there is another question. When you see that left-hand side expression, yeah, so this slide, we need to consider a special concept, exact differential equation. What's this terminology? The meaning of this terminology, exact differential equation. Yeah. So the exact differential equation, yeah, so we continue from the previous slide. Yeah. So when we consider a differential equation, ODE, in this form, okay, we want to determine if the left-hand side expression is exact. What do we mean exact? Yeah, here, the definition of exact is very simple. Can you find a u such that du equals this form? If you can find such u, then we call the left-hand side expression exact form, exact differential form. Okay, all right, yeah. But then there is a question: how do you know if there exists a u function? Right? Yeah. The question: how do you know if there exists a u function here or not? Okay, yeah. So let me ask you this question. Given arbitrary capital M function and a capital N function, can you always find such u function such that the left-hand side expression equals that du? The answer is no. They're not arbitrary function. Okay? Yeah. So then we need to consider the condition for it. Not arbitrary m function and n function. Yeah. Only when m function and n function satisfy some special condition. Yeah. So that condition, so that's our criterion for the exact differential equation. So we need to do that. Okay? We need to figure out that criterion. Yeah. All right. Yeah. Here we need to study the property of the u function again. Total differential, related to the total differential property. Okay? All right. Yeah. Yeah. So implicit type solution, certain differential equation. Yeah. So consider the solution form like this. Yeah. All right. Yeah. So then, yeah. So remember, we want to do the analogy, okay, between the m dx plus n dy form and the total differential form. Okay, the total differential form. Yeah. Yeah. In order to make it happen, yeah, to make it this, this conversion happen, yeah, some special condition should be satisfied. So that special condition we need to look at from the property of the u function here. Okay, yeah, all right. Yeah. So that critical property we need for the u function. Yeah. So there is an important basic theorem in calculus regarding the two-variable function, two-variable function. So that is when u is twice differentiable. Yeah. So here we need to, first we assume this u function is twice differentiable. So you can take derivative twice everywhere. Okay? Yeah. Yeah. Twice differentiable. Yeah. Then after that, under some condition, yeah, because the u has to satisfy some nice condition. Under some condition, then we have this critical property. So what's that? We take partial derivatives twice. Yeah, so you can see partial square. That means you take partial derivative twice. Then the first left-hand side expression, partial x first, then partial y. Okay? The order, the first partial derivative, you do it with respect to x variable. The second partial derivative, you do it with respect to the y variable. Okay, so you get some expression. Then the right-hand side expression, you change the order on the variables. The first time you take partial derivative, you do it with respect to y variable. The second time you do it with x variable. Yeah. So this property tells you if the u function is good enough. Yeah. So I haven't mentioned that good enough property. Yeah. If that u function is good enough, then this equality holds. Otherwise, if u function is not good enough, this equality does not hold. Okay, all right. Then let me tell you, what do you mean? What's the meaning of that good enough? Okay, all right. Yeah, so then when you have this property, then if we go back, yeah, so here we assume if we already have this important relationship, then if we take partial u over partial y, we get the partial second derivative. That expression, partial n over partial x, we get another second partial derivative. Yeah, but based on the critical property, they must be the same. Partial m over partial y and the partial m, they must be the same based on this critical property. Okay, so that's the criteria for m and n function. That's the criteria for m and n function. Yeah, all right. If this criterion is not satisfied, then you cannot find such m and n. Yeah, but there is one special condition we need to consider. Yeah, make sure you have that condition. So that's about what do you mean u is good enough, right? Good enough is if the second partial derivatives are continuous. the second derivatives of u function must be a continuous function. So no breaking part. Okay? Yeah, so continuous. So, you know, connectivity everywhere must be connected. Yeah, no breaking parts. Yeah, yeah, continuous function. Yeah, yeah. So it's under this condition. So then we have the critical property. So then we have the criterion for the exact differential equation. Yeah. So then there is a possibility to find the suitable u function. But you have the possibility. The question is, how do you find that u function? So our next step, we assume both m function and the n function satisfy the criteria. Yeah. So how to find such u function? After we find the u function, then we get a solution of the ODE. Yeah. So the last step. Yeah. All right. Find u with exactness. Yeah. Yeah. So this condition makes sure the exactness of the given form, that m times dx plus n times dy equals 0, that form. Okay, all right. So yeah, so we assume the exactness is there. Yeah, so to find the u function, yeah, the idea, yeah, so pretty straightforward. Yeah. Yeah. To find that u function, we just solve differential equations. Yeah. All right. Yeah, but here we have two differential equations, right? Yeah. So the first one is this differential equation. Partial u over partial x equals m function. M function is given. Okay? M function is given. Can we find some representation of that u function based on this partial derivative? At least we can get some information, right? Yeah, we can get some useful information, at least. Yeah. The second equation, yeah, so we can get more useful information from the second equation, right? Yeah, partial u over partial y equals m function, also given here. Yeah. All right. So here, let me give you the general procedure. Okay, the first form of u, we just take the integral, both sides, but with respect to x variable. Yeah, the partial derivative is applied with respect to the x variable. So when we do the integration, we also do it with respect to x variable. Okay, yeah. So remember, m function is known. Y we treat it as constant. Okay, when you see y, yeah, just treat it as constant. Okay, yeah. All right, then when we take the integral, we need to add some constant term, right? Yeah, this last term is supposed to be a constant term, but since we treat y as constant, so the constant term, the more general case, the constant term may contain y terms, right? So for that reason, this little k function is an unknown function to be determined. Yeah, yeah. But we leave it there. Okay? The little k function, it may contain y terms, but we need to determine this function later. Yeah. All right. So we get a first possible representation for this u function. Yeah. Then next we have second partial derivative. So we can take integral with respect to the y variable. Yeah. So dy, this time we treat y as variable and we treat x as constant. Yeah. Yeah. Then for the constant term may contain x variable. Yeah. So here we use the little l function to represent the constant term with respect to x variable, and this L function is to be determined. Okay, yeah, all right. Yeah, so these two forms should be the same, right? So one same function has two different representations, but these two representations must be the same function. Yeah. Yeah. So with this relationship, we hope we can figure out little k function and the little l function. Yeah. All right. How to do it? How to determine little k function and the little l function? Here, it's not very hard. So let me give you the standard way. Yeah. The standard way to determine k function and l function. Yeah. We just take partial derivatives on equation 1 the first time, on equation 2 the second time. We can get some information about little k function and the little l function. Yeah. Let's do it. Yeah. Yeah. But this time we take partial derivative on y, right? Yeah. Partial u over partial y on equation 1, and a partial u over partial x on equation 2. Yeah, okay, yeah. Because in that way, we can get more information about little k function and the little l function. All right. So when we do that, on the first equation, we get k prime of y equals, yeah. So the integral of m function with respect to x variable, then the whole thing, partial y, yeah, equals m function, yn function, remember our assumption, m function, right? So here, remember, yeah, that's the assumption of m function, partial u over partial y, okay? Yeah, so you can see, because m function is known, so this partial derivative also known, that means k prime function is known, right? K prime function is, can you find the k function? Yeah. Although with some constant. That k function should contain some constant. But the variable part is clear, right? Variable part can be determined. Yeah. Only there is a small constant part to be determined later. All right. Then, similarly, for the second equation, we apply partial derivative with respect to x. Yeah. So little l prime of x equals this integral function over partial x. It's known, right? Yeah. The right-hand side, m function, also known. Yeah. Then L prime function is known, so we can find an L function, little l function, containing some constant, another constant. The variable part can be determined, right? The variable part can be determined. Yeah. So this is the standard procedure. How to determine that u function. Yeah. Although the standard in this way, yeah, but later I may show you. So there is a shortcut. There is a simpler way to figure out little k function and a little l function. Yeah. Simpler than the standard method. Yeah. All right. Then the last thing we will do in this class, in today's class, example for exact ODE. Yeah. I'll show you one simple example to go through the whole procedure. All right. Let's solve this differential ODE. Yeah. This ODE. First, we need to check the exactness, right? Yeah. Otherwise, if it does not satisfy our criterion for the exactness, we have to stop. Okay? Yeah. Because our standard method to determine U function won't work. So we have to stop. Although here I said we have to stop, but later we have some extended method we can apply to rescue. So there is a chance to rescue it. Yeah, but that's the later content. Yeah, we will be there. Yeah. All right, but here we need that exactness condition first. Yeah. So let's check it. Yeah. First, we write n function explicitly and n function clearly here. So the first thing, let's test for exactness. Yeah. By checking the criteria, partial derivative criteria. Yeah. Let's calculate partial m over partial y. Yeah. So we get a negative sign of x plus y. Okay. Yeah. Easy. Yeah. The second, partial n over partial x. Yeah. Because the second time you treat x as the variable, then all the y terms all gone, all become zero when you take a partial derivative. Yeah. So you get a negative sign of x plus y also. Okay. Yeah. So then your conclusion. Yeah. It is exact. Yeah. The given ODE is exact. Yeah. So we have a chance to find that U function. Yeah. So we can apply our standard method to find that U function. Okay. All right. Next, yeah. The first step, yeah, we take the integral on the m function with respect to x variable. Yeah, that's easy. Yeah. Because m function is known. Okay, so it's a sine of x plus y plus little k of y. This k function to be determined. Yeah. All right. Second, u can be written as integral of m function dy plus the L function. Yeah. So the integral part, it's easy. Yeah. So we use y as the variable, so we can do the integral term by term. Yeah. So we get a y cubed plus y squared plus sine of x plus y. Then we have that little L function to be determined. Yeah. All right. Then to determine little k function and a little x function, yeah. So here, first, let's look at the standard method. Then I show you the shortcut. Yeah, very easy shortcut method. So for the standard, yeah, because we need to calculate partial u over partial y on equation 1. Yeah. So this is equation 1. So this is equation 2. All right. Yeah. Yeah. So then we do the partial u partial y on equation 1, so we get this form. Okay. Then because the cosine term left hand side, right hand side can be canceled out, then we have the y prime representation. From the y prime representation, you take integral, simple integral. You can get a y of k of y equals y cubed plus y squared and you need to use a constant C1. Yeah. The second step, this time you apply partial U over partial X on the second equation. Yeah, partial on the second equation, so you get that. Yeah, equals. Yeah, so left hand side, right hand side cosine term cancel out. So you can see little L function is just a constant C2. Yeah. Now you can go back to the U form. When you go back the U form, you write the variable part. Yeah. There are two expressions, but their variable part the same, right? Yeah. The variable part the same. The constant part slightly different. Okay, slightly different, but it's just a constant, right? Yeah. So the constant part it's a constant. Yeah. All right. When we write the final solution, the constant part, because the left hand side will only write the variable part. Because the right hand side there is a, whole constant. So we use C. Yeah. So this is the final solution in the implicit form. Final solution. So that is the solution for our original ODE. Okay? Yeah. So we find a solution. Yeah. All right. Yeah. Before I finish today's class, let me show you the shortcut. Yeah. Yeah. So shortcut to determine little k for k function and L function. Okay, yeah. Actually, we can find k function, L function quickly. Yeah. So we do not need to do partial derivatives twice. Yeah. In these two steps. Okay. Yeah. So, yeah. So let's closely examine these two formulas. That's the first expression and the second expression. Because these two expressions correspond to the same U function, right? That means these two functions should be the same, right? No problem. Yeah. But when we look at the sine term, they both have the sine term, so we don't worry, right? The sine term appears in both expressions. Yeah, so we're fine with that. Then let's look at the variable part. There are y cubed plus y squared. Only y terms, right? So the y terms you can see should go to that little k of y. Yeah. That little k function should contain all these y terms. Yeah. All right. But in the first expression, there is no x terms, so little L terms. So we do not need to put in any variable x terms. Yeah. All right. Then, when we write a solution, we only write the variable terms that appear in two expressions. Okay, without overlap. All right. Yeah. Yeah. All right. So at the end, when we write the final solution, sine x appears both sides. We just write sine function once. Okay. Yeah. So we don't want to duplicate. Yeah. So that's the common terms. First, let's copy the common terms. All right. Then, second, all the variable terms that appear in one of the expressions, we should copy. Okay. Yeah. 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 All right. So all the variable terms, related to x terms, y terms, we copy them. Okay. All right. Yeah. After that, the right hand side, we put a constant c. Yeah. So this is the shortcut. Yeah. So you only use your eyes to examine the terms. Okay. Yeah. So you do not need to take partial derivative. Yeah, it's very effective. Okay, very easy. Yeah, so that's the shortcut method. Yeah. All right, so let me stop right here so we complete this topic.